This time, we will explain RC circuits through an experiment. Currently, what is displayed on the screen is an oscilloscope, a 3300 microfarads capacitor, a 2000 ohms resistor, a switch, and a 3 volts battery. The oscilloscope is measuring the potential of the red point relative to the black point, with the horizontal axis representing time and the vertical axis representing potential. Currently, the switch is off. After turning the switch on, let's use the oscilloscope to observe how the potential of the red point changes relative to the black point. A magnified version of the oscilloscope screen is displayed in the center, so please take a look here if you would like. Now, let's turn the switch on. You can see how the potential rises once and then decreases over time. Currently, the horizontal axis is set to 2 seconds per division, and the vertical axis is set to 1 volt per division. In fact, the shape of this graph can be theoretically predicted with a good degree of accuracy. If the direction of the arrow is positive, the current flowing through the circuit is IT, and the charge stored in the capacitor is QT, then Kirchhoff's second law gives us V equals RIT plus QT over C. Here, IT is the time derivative of QT. If we solve this differential equation with the initial condition Q0 equals 0, assuming that the time the switch is turned on is t equals 0, the solution Qt will look like this. Next, we differentiate both sides with respect to time to find IT, and multiply both sides by R to find the potential difference RIT across the resistor like this. Furthermore, if we substitute V equals 3 volts, C equals 3300 microfarads, and R equals 2000 ohms into the right-hand side of this equation, the resulting RIT is 3 times e to the power of negative t over 6.6. Now let's compare the measured graph with the theoretically calculated graph of RIT. The graphs have almost the same shape, and we can see that the theory is able to explain the phenomenon well.